All right, thanks, Bruno, and thanks to the organizers for this nice opportunity to talk about this work here. It's on mixed order and multirate variational integrators for the simulation of systems which exhibit dynamics on different timescales. And it has been done together with Theresa Wenger and Tobias Geil, who are and have been PhD students in Erlangen, and of course during my long-term cooperation with Sept. So the price we usually pay for accuracy when doing numerical simulation is runtime. And there are two strategies. One is to have a low-order method and just put it on a finer grid, and we see the behavior here. Or on the other hand, one can increase the order of the method, and that's what these slides will show. And there's usually some point where one or the other approach is more advantageous in terms of computational costs. On the other hand, structure preservation is of course important. I don't need to tell to anybody here. So sometimes even cheaper methods are able to represent the unique fingerprint of a system better than methods which invest more computational effort. So the systems we would like to look at in this talk are systems exhibiting dynamics on different timescales that come, where this fact comes from different stiffnesses in the potentials. So these might occur, for example, in astrophysics, but also in molecular dynamics. But in particular, in the environment where I'm working, we are often concerned with multi-body systems that can be prosthetic devices or robotic systems where, let's say, rather stiff or rigid and other compliant parts are put together. And the two approaches I would like to present here today, they are both based on variational integration. One is a mixed order approximation, and the other one is an approximation on two different time grids. So in literature, you can find, of course, a lot of methods that are suitable for these types of problems. And a famous, well, let's say one idea is such an implicit-explicit splitting method, or it's also around by the name, well, it falls into the class of impulse methods. And a prominent example by somebody who's sitting here today, by Ari, is this IMAX integrator. And this will pop up during the presentation again and again. So on the other hand, if we have systems where we a priori know which are the fast and which are the slow parts, one can separate these and do so-called multirate integration. The extreme would be a kind of a co-simulation where you even have not just different methods, but maybe different software tools or different spatially separated machines where to simulate and then synchronize it sometime. On the other hand, averaging methods are around. They are not interested in resolving the fast dynamics, but take an average and feed it into the slower parts. And one example is also this heterogeneous multiscale framework, let's say, and flow averaging integrators. And these are already an example which is formulated in a variational way. So a very short glance at the main idea of variational integrators, which lead to structure preserving schemes in the sense that we have in the discrete setting symplecticity, a discrete Noether theorem, ensuring the preservation of momentum maps if there's symmetry, and of course backward error analysis leads to the good energy behavior. So variational integrators are really flexible, let's say, and one can adapt them or design them to the features that different problems have, and also to the demands of the numerical simulation. And this is a by no means complete overview, just to mention a couple of works where variational integrators are used, ranging from holonomically or non-holonomically constrained systems over PDEs, non-smooth systems, leak group problems, stochastic problems, and in particular higher order methods can be designed to lead to more accurate solutions. So let's have a look at the formulation of the continuous problem of dynamics of a system with dynamics on different timescales, and assuming that we a priori know which part of the configuration variable is moving slowly and which one is doing the fast motion. And we assume that we have a potential which can be also split. Here this represents a slow potential, which is probably a little bit more nonlinear and maybe more costly or expensive to evaluate, depending on the full configuration. And on the other hand, there's the fast and relatively stiff potential, which might be a bit cheaper to evaluate. Further on, holonomic constraints are considered here in this formulation from the beginning, and they might apply just to the slow part or couple the slow and the fast part. And we can just as well have constraints just depending on the fast variables, but they don't introduce any new interesting things, so this is why they are left out here. And we have Hamilton's principle leading to this type of Euler-Lagrange equations. Now one can of course formulate properties of this system. In particular, the Lagrangian one form here can be additively split into a slow and into a fast part. There's a symplectic form which is preserved by the Lagrangian flow, and one can easily show this by using the generating function argument, showing that the total differential of the action integral has this form where we have the conjugate momenta of the slow and the fast part derived via Legendre transformations. And one can also, more or less in the standard way, show that there's a Noether theorem. Here it's formulated for group actions acting on the slow and on the fast part separately, and then one can show that there's momentum maps according to these conserved, but you can of course formulate it also with a group action on the entire configuration, and then it's just a standard form. Right, so now the idea how to approximate the solution of these systems with higher order constraint variational integrators is to choose some polynomial of degree s here. It depends on s+1 configurations then, and is defined with control points which are denoted d here. And then for the Lagrange multipliers, one can choose a polynomial of different degree. And if we have a system where we a priori can separate the configuration variables, then we can even choose different polynomial degrees. One here for the slow part, it's denoted by PS, the other one for the fast part denoted by PF. And we have, of course, control points for the polynomial approximations, and just the same here for the Lagrange multipliers. Now all these different degree polynomials are inserted into the Lagrangian function, and we need an approximation of the action integral. Therefore, quadrature rules are essential, and basically every part can be approximated by a different quadrature rule. So the kinetic energy part has a quadrature rule of order OT, then the stiff potential one has another one, then the slowly moving potential. And also the constraint terms here can have their own quadrature rule. So now we have 4 different degrees of potential and 5 different quadrature rules, which gives great flexibility in the design of the method. However, these combinations cannot be chosen completely arbitrarily. They are subject to certain conditions. And let's start with conditions that are relevant in particular in the constraint case. So the the quadrature points to approximate these integrals over constraint functions times multipliers need to be part of the control points of the Lagrange multiplier polynomial in the slow and also in that fast case. Why? Only then it's ensured that the number of unknowns in the total system is equal to the number of equations. Further, to ensure that this right number of equations is also a set of independent equations, one has to fulfill conditions on the combinations of polynomial degree. So in case of using Lobato quadrature here, we need the polynomial degree of the configuration approximations to be greater or equal than that of the Lagrange multiplier polynomial to ensure linear independence of the equations. And why are we just looking at Lobato here? Well, to get a stiffly accurate scheme, which means that constraints are fulfilled on the grid of the time node and not somewhere in between on the polynomial, only Lobato quadrature is possible for these terms here. Okay, so let me show you a very first example. This is this triple pendulum, and there's even a little movie that gives you an impression on the combination of slow and fast motion. But it's just a triple pendulum, and it's made a little bit more nonlinear here by this type of potential. And if we look at this plot that gives the energy error over runtime, we can see low-order methods here based on linear polynomials and Gaussian quadrature or a Gauss-Lobato combination here. Now, if we want to have better accuracy, we obviously increase the polynomial degree, in particular in the fast part, and also the corresponding quadrature. So if you look at these three lines from orange, purple to yellow, we always have third order quadrature, third order polynomial for the fast part. But it's getting a bit cheaper if we decrease the slow polynomial. So it goes from 3, 2 to 1, and this curve is not much more inaccurate than the other ones, but it has shifted to the left. So it means that computational time has been saved in this way without losing accuracy. And of course, the variationally derived scheme is structure preserving. So here we see momentum preservation up to the numerical accuracy, which is close to that used in the Newton iteration. And one can also show all the other parts, symplecticity, there's a discrete Noether theorem. And for symmetric quadrature and control points, the scheme is also reversible in time. So these are not the only conditions that I just mentioned, leading to the right number of independent equations, but one should also think about well-definedness. And this is now looked at, first of all, for such a separable Lagrangian with just dynamics on one time scale. There used to be this result by Hall and Liog, stating that the number of quadrature nodes in the Gaussian case has to be greater or equal to the polynomial configuration polynomial degree. And in the Lobato case, there has to be one more quadrature point. Now, one new little result is that this extra quadrature point is not necessary. So that's a sharper bound now. Well-definedness follows already for the Lobato case if the polynomial degree and the number of quadrature points are equal. And this will show later on that we can also talk about the well-definedness of Lobato 3AB methods. It will come up in the next slides. Just by they fall into this class here and fulfill this sharper bound, whereas they would not have fulfilled the other one. And in the case that we have multirate dynamics, so dynamics on different timescales, as just discussed, one can translate this condition just to the conditions on the quadrature rules that you can see here. So it's difficult to derive sharp bounds for the well-definedness. And one way, if you just look at a combination of polynomial degree and quadrature rule, it's difficult to do that. But one way around would be the relation to constrained symplectic Romer-Kutta methods, where, for example, where maybe other statements are known. Okay, the general case is described here. Let's look at some particular cases. So if we choose now for the constraint case, the polynomial degree of the Lagrange multipliers one higher than that of the configuration, and use Gaussian quadrature, we have the higher order constraint variational integrator being equivalent to this S-Gauss method of convergence order to S. However, that one is not stiffly accurate because there's Gaussian quadrature everywhere. If we use the same polynomial degree for multipliers and configuration and enrich the system by the hidden constraints on velocity level, we arrive at this Gauss-Lobato spark method of convergence order to S. And if we have the degree of the Lagrange multipliers one lower than the configurational one and use just Lovato, then the variational integrator is equivalent to this constraint S Lovato 3AB pair of convergence order 2S minus 2. And the low order representative is the Rattle method here. Okay, now for the case where we have the number of quadrature nodes, one more than the polynomial degree of the configuration, Sina has shown in this work here that the resulting variational integrator is equivalent to this modified Runge-Kutta scheme. And if we have separable Lagrangians, it can be transformed into this S plus 1 Lovato 3AB pair, and we know convergence is of order 2S. Now Teresa has been able to generalize that result to the case that we also have constraints in the system. So we have equivalence to the modified constraint modified Runge-Kutta method, and for the particular separable Lagrangian, equivalence to such a constraint S plus 1 Lovato 3AB pair. Now the remarkable point of this equivalence is that the Lovato method is based on an S plus 1 degree polynomial, whereas we have an S degree polynomial in the variational integrator case. Nevertheless, the equivalence of the methods means that at the grid points and at the stages, they really take the same values and they have the same convergence order. However, we can obtain that approximate solution with one unknown less in the variational integrator case compared to the Lovato case. Okay, that's the constraint modified Runge-Kutta scheme to which this integrator is equivalent. Let's not go through any details here right now, just that it has been shown once. The next point I would like to talk is linear stability, and this is analyzed now in a way which is a little bit different from the usual investigations on the propagation matrix, but it's very well suitable for the formulation of the variational integrator. And we start to look at unconstrained single timescale system here, the harmonic oscillator obviously, and the discrete Euler-Lagrange equations from the variational integrator can be written in this form with a matrix A. This depends on the product of time step and frequency. Now, assuming that this matrix is invertible and bisymmetric, one can rewrite the propagation matrix in terms of subdeterminants of this matrix A.
What means the matrix is bisymmetric?
It means it's not symmetric with just the one diagonal, but also with respect to the other diagonal.
Symmetric with respect to the empty diagonals.
Okay.
Okay, thanks. So the traditional stability conditions that come from the propagation matrix investigation are then replaced by linear stability conditions that are either formulated in this way or equivalently in that way. And I would like to use some examples to demonstrate that same stability results are obtained, but there's not a theoretical result yet. So if we analyze the case where this matrix has determinant 0, that's exactly the cases where there's an orthogonal propagation matrix which plus and minus ones here, which is a stable scheme but useless, of course. And the other case that comes out of this is an unstable, shows instability also when analyzing the propagation matrix. Now, just for the Stemmer-Verlet example, I would like to demonstrate that one really gets the same condition for stability here. And on the other case, for the Gauss collocation methods, which are unconditionally stable, there are still two cases where the propagation matrix takes this or that form, And these are precisely cases which can also be identified by analyzing this matrix A. And this plot here just represents the critical combinations of time step and frequency which are determined by that analysis. Now, if we go to the case of split potential for dynamics on different time scales, with the harmonic oscillator being modified a little bit, we did this analysis of this matrix A. And here you can see an illustration of this condition here for different combinations of quadrature. So we have the slow polynomial of degree. We have a polynomial degree 3 and different order quadratures. Here Lobato with order 2 and here Lobato with order 6. And the curves lie really on top of each other. And if we enlarge this critical region here, we can see that the instability region is only slightly larger for the lower order quadrature, which means for the cheaper scheme. So the message is that we do not really lose any stability by going to a cheaper method here. And if we additionally split the configuration variable and go through the same type of analysis of this matrix A again, first of all, it also comes in quite handy to build up the propagation matrix, because the propagation matrix is determined by 7 subdeterminants of this matrix A. And here we have the linear stability conditions. And on this slide again, visualized how these conditions are fulfilled with different combinations now of polynomial degree 3 for the fast motion and varying polynomial degree 1, 2, and 3 for the slow part, and also different quadrature. And the message is the same as before. These curves lie on top of each other. So the stability regions differ slightly or not at all between these different schemes based on different polynomial degrees for the slow part. And stability is, of course, one important question. The other one is how well is the energy behavior captured. And there, modulated Fourier expansion is the tool of choice to analyze how well the total or the oscillatory energy is captured by the simulation. And again, by Hairer, Lubich, and Wanner, there is this trigonometric integrators that are shown to conserve total and oscillatory energy up to the order h, being the time step. And now our scheme for the case, choosing some fast polynomial degree and having the slow polynomial degree smaller or equal to that, plus a combination of this low order Lobato and maybe higher order Gaussian quadrature, this mixed order variational integrator can be written in form of such a modified trigonometric integrator, where we have another reference here by R. So then we rewrite the scheme exactly in this form and know that for abbreviations alpha, beta, gamma of these complex expressions here, the condition to capture energy correctly is that all these alpha, beta, gamma have to be equal to 1. Now for the scheme just presented, the mixed order variation integrator with this combination of degrees and quadrature, they do fulfill the first two conditions. Alpha and beta are always equal to 1. The third one is fulfilled if there's this additional relation between time step, original, and modified frequency. And this is fulfilled precisely if we also have a linear polynomial for the fast configuration. Then we are in the IMAX case, and there it's fulfilled for any combination of time step and frequency. On the other hand, for this mixed or higher order scheme, if we have a quadratic polynomial in the fast configuration, there's only particular combinations which fulfill this condition. However, If it's fulfilled, then the energy behavior is captured even better. Right. This is illustrated now with the help of this famous Fermi-Pastor-Ulam example. There are 2L masses linked with alternating soft and stiff springs. Now, if we simulate the system with this mixed order variational integrators with different combinations of polynomial degrees, we can see here now that this is the one where we have linear polynomials everywhere, so that's Imax. This is the one having a linear polynomial in the slow and the quadratic one in the fast part, and that one has a cubic one in the fast part. And we can see exactly these estimates here. So the first and second order fast polynomial have better conservation of the energy in the fast spring. So we have smaller oscillations here compared to this case where these are of the order h. Also, let's have a look at the behavior in terms of error versus runtime. Here you can see different lines. The low order method, the very low order methods do not converge at all. This is because we have a long-term simulation here, and the known phase shifts which are introduced by the Lagrange multipliers at a certain point take over. So, and once the phase shift is by anticyclic to the period, right, you can, the error does not get better anymore. However, the higher order methods behavior you can see here, and I would say from a practical point of view, you can choose for the accuracy that you need the fastest method from such a plot. So now, so far, we have seen the first part that was having different polynomial degree approximations and different quadrature combinations, but all on the same time grid. The second approach would be to just stick with linear polynomials in the slow and in the fast part, but simulating the system on such multiple time grids. So there's a macro time node, which is denoted delta capital T, subdivided into the number little p micro time nodes, and this means that we work with a synchronized grid here. That's important when we want to analyze conservation properties. We need to have synchronization points in the system because we cannot expect the conservation of a property somewhere in between where we just have the polynomial, let's say, but not the solution determined on the grid node. Okay, the idea is the same. We have well, the slow and the fast variable, and also Lagrange multipliers in case that the system has some holonomic constraints. Now the machinery goes on, let's say, so everything is inserted to have an approximation of the action integral over the Lagrangian and also of that part over the constraints times the Lagrange multiplier. And of course, again, quadrature rules will be needed to define the precise scheme. And again, here we cannot use some Gaussian type quadrature, but just Lobato type quadrature, or let's say trapezoidal rule, the low order representative, to be able to ensure constraints on the time node itself. Okay, that's the discrete Euler-Lagrange equations. Just to show them once, they obtained from the discrete variational principle. And what are the properties? So, again, one can derive Lagrangian one forms, and as typical in the discrete setting, there's a plus and a minus form, and for this multirate setting, they are composed by a slow and a fast part. Then there's a symplectic form, just one of them, a discrete symplectic form, which is preserved by the discrete Lagrangian multirate flow. And this statement can be proved by the generating function argument again. So the discrete action really is a generating function for the discrete Lagrangian multirate flow. Further on, there's a discrete Noether theorem, and again, it can be formulated in such a separate way where we have groups acting just on the slow or just on the fast part of the system, leading to such separate momentum maps, but of course we can formulate it in a unified way. Just imagine that the slow and the fast action are the same and act at the same time, and then we get the usual formulation and the discrete momentum map, which is of course conserved. Everything depends on the quadrature. So what the scheme is like depends on the choice of quadrature. And here are some examples. So this is called a midpoint quadrature in the fast part, because the midpoint of the configurations is taken in here. And depending on what midpoints these should be, whether these should be midpoints of the macrogrid or the microgrid, it might be necessary to introduce also some interpolation of the slow variables to put it on the microgrid. Okay, so here's one variant, midpoint, slow and fast on the microgrid, and another variant that uses midpoint just in the fast potential, but in the slow potential, a trapezoidal rule. And if this is chosen with alpha equal to 1/2 and with p equal to 1, so no micro grid, just one tiny grid, then we are back at Imax again. Another variant can be seen here. So this is a trapezoidal rule in the slow and in the fast potential. But if we go now to trapezoidal rule just on the macrogrid, as you can see it here, that will lead the scheme which is explicit in the slow forces and implicit in the fast ones. And remember that in the beginning it was said that it might be that this lower potential is a bit more expensive to evaluate, and then it might be very useful to have a variant of the scheme which is explicit in these forces, so you don't have to evaluate them again and again while solving iteratively. And of course, one can formulate fully explicit variants as well. That's something based on a trapezoidal rule also on the microgrid. Good. Now, what about the analysis of these multirate variational integrators? So, as you are all aware, for variational integrators, we have a variational error analysis, which is based on the idea to check how well is the real action integral approximated by the discrete Lagrangian. And then the theorem here states that the approximation of the discrete Lagrangian to the real action here has the same error as the discrete Lagrangian flow, and also the discrete Legendre transformations have the same error. So in particular, if we have this approximation being of order R, we have an order R method. So for this multirate variational integrator, the following theorem states that for particular combinations of quadrature, we get the errors that you can see here. So that's for probably not super surprising. I mean, if we have midpoint approximations, we get a second order scheme. If we use rectangular quadrature rules, so just evaluating at the one or the other end of the time interval, that reduces the order and we only have first order convergence schemes. And these results have been obtained by Taylor series expansion of the real action in terms of the slow and the fast state variables, and Taylor series expansion of the discrete Lagrangian in the multirate case, and then of course using theorem 1 stating that the approximation between these two gives us as the same error as the Lagrangian flow. So one can think about two different ways of refinement for these multirate integrators. So the standard way would be to have a constant number of microsteps per macrostep, and then to refine the whole grid by the same amount. And this is what is you see here, and if one can easily show that if this is, well, we have order of convergence to q minus 1 if we have these errors as just stated here above. On the other hand, you could think of keeping a constant macro grid, but refining just the microgrid. So using more micro time steps per macro step, that would mean to have this number p getting bigger. Of course, you don't have convergence, because if something is not refined, you cannot have the overall scheme being convergent. Nevertheless, for practical applications, it might make sense to do that to a certain extent, because the accuracy that you get for the slow part might be enough, and you want to well, you might be able to decrease the overall error by just decreasing the micro time step, but of course you cannot get to a fully convergent scheme. Okay, for the error plots I'm showing in a second, here are two definitions. So one is the error on the synchronization points of the grid, of the full configuration variable. The other one is an error on the microgrid, just of the fast part of the system. But before we look at the plots, let's look at the linear stability question. So this is answered here for Lagrangian, discrete Lagrangian, using a trapezoidal rule for the slow potential and the midpoint or trapezoidal rule for the fast one. And the multirate variation integrator is reformulated in such a kick, oscillate, kick form. Kick means just according to the slow potential, then we have an oscillation according to kinetic energy and the fast part, and another kick. Now, the theorem states that this variational multirate integrator is stable if the macro and micro time step are small enough such that the kick and the oscillate part are stable in themselves. And then there's an additional condition here that the macro time step is not near such integer multiples of pi times this modified frequency, which is defined like this or like that in the case of midpoint and trapezoidal quadrature. So that means that well, this is now found in with the analysis of the propagation matrix, and it means that we get more and more instabilities the more micro steps per macro step we use. And there's, for this midpoint scheme, p minus 1 instabilities, and for the trapezoidal one, p instability.
With the resonances somehow?
Yes. However, as you can see also from the way it's written here, if you have p equal to 1, that's the IMAX case again, 0 instabilities. So that one works as a charm. Okay, modulated Fourier shows again, IMAX works as a charm. Because, well, let's say we do it for this combination, midpoint fast, trapezoidal slow, reformulate the multirate VI as a modified trigonometric integrator, and get conservation of the total and oscillatory energy up to order of the macro time step, but for all p greater or equal to 1. So energy behavior is captured also, but if we really have a microgrid which is different from the macrogrid. However, we get better conservation for p equal to 1. So 2 examples, the Fermi-Pastor-Ulam problem shown before, and this is such a spring ring, which is just a 3D generalization, which we did with the goal to show conservation of momentum maps according to Noether's theorem, because only then we have, let's say, a real symmetry, and we can look at angular momentum conservation of the system, which is impossible here. Okay, these are the plots just for the FPU, and we see confirmed the convergence orders that have been theoretically derived, of course. Good for p equal to 5, 10, And this table is just a summary. So we have the expected convergence orders in relation to the midpoint or rectangle quadrature rules for both examples. What about computing time savings? So we can see for the Fermi-Passer-Ulam problem, we do save time by increasing p. Now this is done in the following way. We fix a micro time step, so we fix the accuracy of the fast part according to, let's say, the need of the simulation. Then p is increased, meaning that the macro time step is increased, which makes the whole simulation cheaper because the number of slow variables is decreased when the macro time step is increased. And we can see that this saves computational costs, however, only until a certain point. We cannot increase p infinitely, and what the reason is, on the one hand, the saving comes, among other things, from a strong reduction in the number of iterations which is necessary when solving the system. So that it decreases with p. On the other hand, the system which is solved in one time step, so this investigation has been done for kind of a long-term simulation, and with a larger number of p in every macro time step, which has to be solved at the same time, let's say, we have more micro steps in, and there is a larger dimension of the system. And that is expensive, in particular in terms of the evaluation of the Jacobian or the tangent matrix. So the message is we get savings, but not unlimited. And the same is shown for this more complex example here. Okay, it's also meant to illustrate a little bit what is, for the choice of parameters we made, we have slow and fast motion. And I think now I have a problem because I don't know how to close it. Because, because this is not as it was. Let's see. Moment. I don't know if this. See, it's still not doing it. Excuse me. Oh no. But that's that might save. No, you don't want to report that anywhere. No. Excuse me. So, but reopening might save the situation. Where were we? Okay, not pressing it again. And just showing, looking at that plot again here, we get savings, but at a certain point we cannot save more. Right, so for the final 30 minutes? No, okay. I would like to talk a little bit, but just briefly, about the use of structure-preserving integration in optimal control simulations. And to motivate optimal control simulations, a popular example is the Hubble telescope, where external momentum wheels, there's torque applied, and then the system reorients, just as in this model here. And due to the fact that, let's say it from an engineering point of view, you apply the same amount of torque with different sign to the main body and the momentum wheel, the sum of torque is 0, so angular momentum shouldn't change. To say it more geometrically, this system reorients due to a geometric phase. So there's 0 angular momentum all the time, and we have this reorientation. And the structure-preserving method used for the optimal control simulation is able to represent this behavior correctly. Further, if we have a non-structure-preserving method, we are not so sure about the translation of the applied control into motion as we can be here in this case. Now, that's a general form of an optimal control problem. minimizing some cost functional with respect to the state and control trajectory subject to system equations and initial conditions. And the main difference between an indirect and a direct method is the order of the optimization and discretization steps. So indirect methods first optimize, then discretize, and it's vice versa in direct methods. And of course, naturally, the question arises, when do these steps commute? And secondly, if we choose a direct method, where the state equations are discretized and the rest of the scheme evolves through the optimization, what is the resulting order for the control and the adjoint scheme? And there's a beautiful theory one can go through. This works of Bonan and Hager, and of course of Sancerna and of Sinas, that I cannot go into detail, as much detail as I would like to know, but let's just summarize that symplectic methods are the link in between the direct and the indirect way, in the sense that we get a symplectic approximation by using this, by doing the optimization in the direct way. And furthermore, if the state equations have been discretized in a symplectic way from the very beginning in the direct side, then there's whole scheme is double symplectic, as it has been stated. So we have the state, the adjoint, and the control scheme being the same, and they are all symplectic. So in particular, of course, we get the same order of convergence of all these variables. So now it's clear what is the next step: to do the multirate variational integrator, to use that in the framework of discrete mechanics and optimal control. For the optimal control of the upswing of such a system here, which has a slowly moving and a fast moving part. And I'm not sure if I should show the movie. The same thing might happen again, so I will not do it. But you believe me that it's a slow and a fast motion. You can also see here the slow angle that evolves for the upswing and the faster angle oscillating a little bit, and that's the control trajectory. And due to the symplecticity in the whole scheme, we have the same convergence order for configuration, momentum, and also control, and also the adjoint, which is not shown here. And the point I want to make is that there's also computing time savings, because in the optimal control setting, where direct transcription methods are used, you have the complete set of time-stepping equations from the beginning to the end time as your site conditions. So it's not as in forward dynamics, where you have maybe a macro step with micro steps in between, or many control points of the polynomial, but still you go forward only one time step. But in optimal control, you have your simulation interval and the complete set of system or discretized system equations which needs to be fulfilled at once. And there, of course, the dimension of the system plays an even more important role, and to reduce it is kind of crucial. And we can also see here that using this multirate idea and having p micro steps per macro step, computing time is really reduced. Okay, these what I show now in the end are a couple of other optimal control problems coming from more biomechanical applications, let's say, and also for these, the multirate variation integrators might be useful in the future. So far, they have other challenges, like for example, for the gate problem, you have the impacts and the opening and closing of the contact points between the foot and the ground, and this makes this hybrid dynamical system with a known switching sequence. At least when slowly walking, you know in which order the contact points open and close, but unknown switching times, which is also solved using this DMOC framework here, but doing something to handle this opening and closing, or to handle the hybrid structure. The same hybrid structure is faced when doing CRASP simulations. So let me just try to show you this lateral pinch. So that's a pinch, like if you grab a key or a credit card, and that's an optimal control problem now, where the objective function is physiologically motivated to try to yield such a, let's say, well, what is natural, yeah? But at least you could imagine that you are grabbing a key in a similar way. Ah, good, it vanished. Nice. So, last example, when this is a multi-body system, which is representing an upper and a lower arm, and this is optimally controlled via muscle models, which have certain origins and in certain points on the bones. And these muscles are modeled in such a way that they wrap around the bones. So they can wrap around one body, go through free space, and wrap around the next one. And this is then formulated as a geodesic problem of the muscle wrapping on the surface of the multi-body system. And it can be formulated in a complete variational setting. Here you see complementarity conditions for the wrapping. And then, of course, also the discrete equations, which are used in the direct transcription optimal control method, are derived in a discrete variational way. Okay, and here you see the arm motion controlled, in this case, by just 3 muscles, and different ways how to describe this, the surfaces where the muscles wrap on. Here it's a nerve surface which moves with the multi-body system. And the point I want to make is that this simple system already has about 10,000 optimization variables. And of course it's crucial if you want to have accurate solutions, and if you can make this, limit the system dimensions by using this multi-rate time integration, that's helpful. This one is solved with an interior point optimizer, and global solution is approximated, and it uses automatic differentiation to speed things up. Right, so I wanted to show you in the end where this is planned to be used later on. But the main point here in the talk was, of course, the mixed order variational integrator, the multirate integrator, together with the properties that have been analyzed. And what is maybe still missing is a systematic comparison between the two approaches. Thank you.
Question?
Late in the afternoon. Talked a lot.
What are the, for example, in this gate example, what is the cost function, and what kind of equations do you use for the eggs to move?
Yeah. So the gate problem is formulated as a problem with periodic boundary conditions. So it's just a half step. Let's say I start like this and stop like this with symmetry or periodic boundary conditions. A physiologically motivated cost function for gate, well, it's usually a combination of different, so it's a weighted sum. One is the specific effort, which means the, let's say, control effort per step length. We have the step length in the denominator. Then to make biomechanical motion rather smooth looking, it's a good idea to have the torque change, or let's say the actuation change in the cost function. Because our muscles usually do not jump from 0 activation to 100% activation. So that is very often a key point to do, to have the actuation change squared then. And then you can go much further, depending on the muscle model in use. You can have, let's say, the distribution of muscle forces over different muscles in use according to their diameter or according to their strength, which is known from other investigations. You can even go as far as having the calories that are burned. You can compute them depending on the muscle models. Or there are other models that go as deep as to the ion, as on ion level or on cell level, let's say. It depends. Yeah.
But the equations, so how many parts in the legs do you have, for example, and each of them, do you model the muscles as well?
In this example I showed here, no. Here in this example, these are very simple hill models. So the model consists just of a massless and also stiffnessless parse. It's a geodesic parse. And the muscle lengths and the change of the muscle lengths determine the actual muscle force together with the maximal possible force and the activation level of the muscle. There's these famous force length and force velocity relations, what the muscle can produce. Because you know if you have your arm extended, the force will be smaller compared to if you have your arm bent a little bit and then the muscles are shorter. And you also know from your experience, if you move fast, it's different, the kind of force that you can produce compared to if you move slowly. And there are some well-known functions to describe it.
All right, it's already 4 o'clock, so I think maybe we should thank Sigrid again. She will be here for, both of you will be here for another 2 days, so you will still have the chance to be in the evening. Thank you.
Thank you very much.
Perfect.